Hello friends. So, today we start a entirely new topic which is very different from what we have been discussing so far, and that deals with one of the very powerful techniques of mathematical analysis, that is Fourier transform, and more specifically discrete Fourier transform, because we will be concentrating on the implementation of Fourier transform on digital computers, which often obviously deals with discrete time data. And this process of dealing with discrete time data brings in its own set of peculiarities which need to be understood. And of course, we will also be discussing the algorithm for computing of Fourier transform, why Fourier transforms have become such a powerful technique. It has happened only in the its relatively recent phenomena, only since 1965, when the fast Fourier transform algorithm was discovered, that Fourier analysis and Fourier transforms have really become a powerful tool. Otherwise, Fourier analysis and harmonic analysis as a mathematical tool, they have been known for a very long time, but its practical application was not possible until the discovery of fast Fourier transform algorithm. Fast Fourier transform algorithm is essentially a very efficient way of computing discrete Fourier transforms. So, while there are many algorithms now available in public domain as well as in proprietary format for computation of Fourier transforms, fast Fourier transforms, we will of course discuss the basic idea behind fast Fourier transform algorithm, but our main emphasis will be to understand the discrete Fourier transform. What are the peculiarities and what that happen when we deal with discrete time data, and how it relates to the Fourier transform and Fourier series, its precursor Fourier series that it is based on. So, Fourier series is just another kind of Fourier transform, we may say that. So, every time varying function has an alternate representation in frequency domain. So, the moment we talk about time variance, then obviously it is obvious that we are talking about some oscillations or some variation around some mean position, and that itself implies that there is something to do with frequency as a character. What frequencies or how fast the oscillations are happening across the mean position and so on. So, that is a representation that how the rapidity of crossing the 0 line is what we, or mean position, refers to the frequency of the oscillation. And this frequency domain representation can be a preferred representation in some application. For example, we can have a time domain signal can be very varied, very complex looking time domain signal, and it will have some frequency domain representation analogous to. So, this is a very common representation. Lowercase alphabet is used to refer to time domain signal, and corresponding uppercase alphabet is used to refer to its Fourier transform or frequency domain representation. And there is a one to one correspondence for every time domain signal, there will be some frequency domain representation. And so on, and they may be interchangeable. So, these are all interchangeable representations. So, whatever is there in time domain, the frequency domain representation is just another way of representing it. It is just another way of putting this information in another format, but there are applications of both of them. For example, in frequency domain, we can clearly, while we can clearly identify which frequency components are present in the signal, right. So, this is let us say omega 0, and this is twice omega naught, and this is thrice omega naught, and of course, this is minus omega 0, minus 2 omega 0 and minus 3 omega 0. So, these are the frequencies that are present, and this information, the frequencies that are present in the signal that make up this constituent, this time domain signal, this cannot be inferred from this time domain signature. While what is the maximum value of this time domain signature or the waveform, which is what is often useful for design calculation or for any engineering design and decision making. What is the maximum value, what is the critical worst case scenario, what is the worst possible maximum value that needs to be taken for, I mean for capacity allocation. So, this maximum value, while it can be extracted readily from a time domain representation, we can't really get this information from frequency domain representation. But this frequency domain representation allows me to tell that I am looking at a potential problem if the natural frequency of the system that I design, that I am trying to design or trying to synthesize, if the natural frequency somehow coincides or is in close vicinity with either omega 0 or 2 omega 0 or 3 omega 0, then I am looking at potential trouble spot, because they may involve kind of resonant kind condition, and dynamic response may actually build up to a very high order by very high order of amplification with respect to what is expected for a static response. So, in order to avoid this kind of error happening or this kind of catastrophe happening, we can a priori look at what is the frequency content of the excitation and then take a suitable design call to avoid a natural frequency of the system to be designed to be anywhere in the vicinity of trouble spots in the frequency domain. And secondly, some of the key mathematical operators, for example, we talked about solution of equations of motion by time marching schemes. So, those numerical integration as well as a numerical differentiation and convolution, the system response, linear system response to dynamic excitation. So, that is convolution, and these operations in time domain, they are very time consuming and very tedious, and they become, I mean these operations, these mathematical operations, they become very simple and very trivial. They are reduced to trivial simple multiplication of two floating point numbers in case of frequency domain operations, and that is why it is often possible, and this actually falls in, and this is another quiver, another arrow in our quiver of any person dealing with dynamic quantities or time varying quantities. So, Fourier transform is a very important tool of the trade that can be used. I mean sometimes it becomes very simple or very efficient and very straightforward to analyze a system in frequency domain than it is in time domain. And frequency domain representation allows a better understanding of the dynamic phenomena, which may not be revealed in time domain representation. As we discussed, the frequency composition is not possible to be inferred from time domain representation. The basic principle is, now we are going back to the concept of Fourier series, that Fourier series is used to approximate any periodic function in terms of orthogonal harmonic components. So, it is an infinite series, we all know, we have all studied Fourier series, and Fourier series is an infinite series involving sine and cosine terms, and any periodic function, as long as it is a finite energy signal and with at most finite number of discontinuities within the period, within a period, that can be expressed as a sum of sine and cosine. So, a Fourier series expansion. So, idea is any finite energy or square integrable. So, when I say finite energy, so that means minus T naught by 2 to T naught by 2, where T naught is the period of the wave. So, either I say absolute integrable if this is less than infinity, or another way to say this is a square integrable that will take care of the negative sign, and if this is less than infinity, if this is finite. So, this is actually square integrable. So, this is what we call as a finite energy signal. Energy of the signal is finite. So, any finite energy signal, so this square integrable of finite energy, or it can also be referred to or just taken as the absolute value function, absolute value, absolute integrable. So, as long as the function has finite energy or absolute integrable over one period, the function and with at most finite number of discontinuities, it can be decomposed in terms of orthogonal harmonic components of frequencies, and the frequencies that would be multiples of the period of the function. So, if T naught is the period of the function, the frequencies would be 2 pi over T naught, that is fundamental harmonic omega 0, and then the next harmonic would be twice omega naught, next harmonic would be thrice omega naught, and so on. So, integer multiple of the fundamental harmonic, and that will constitute sine and cosine terms of these frequencies can be used to approximate the function. So, essentially the periodic function, if f of t is the periodic function of t 0 is the period, then it can be represented as a 0 by a 2. So, that is a constant term just to shift the mean position in case, just in case the function has a non-zero mean. So, that can be modeled by using this constant term, and then there are sine and cosine terms of fundamental and higher harmonics. So, j is the representation. So, multiple that represents the harmonic number. So, which harmonic we are looking at, and function f t is such that it is periodic with period t naught, such that t plus n times t naught is same as f of t, where n can be 1, 2 or 3 or anything integer. And the coefficients a j and b j, these are some like generalized coefficients. They represent or they measure the representation or the extent to which individual term, individual base function. So, this is so Fourier series is just an extension of what we have been talking about as a vector space. So, this is in the limiting case as the dimension of the vector space tends to infinity. So, then we are looking at continuous function space, and then these trigonometric functions, they define linear basis functions for the function space, and this is the same extension just as we defined any arbitrary function as a linear combination of basis function, basis vectors. In case of any arbitrary vector represented as a linear combination of base vectors, and we are doing here the same. Any arbitrary periodic function can be represented as a linear combination of base functions, and base functions are trigonometric functions of fundamental harmonic or frequency omega 0 and integer multiples of these frequencies. And coefficients a and j and b j, they are the generalized coordinates, and essentially the inner product of this function f t along these base function. So, essentially projection of function along the base function, and that actually gives us a measure of how much a particular base function, particular trigonometric function contributes to the making of this function f t. So, a j, b j, a j and b j are the coefficients of decomposition representing projection of function f t along the respective basis function, and they are computed as inner product. So, that is how we take, in case of vector spaces we took the dot product, and in case of function space we just take the integral of this inner product over the period of the function. So, a j are defined as f t multiplied by cos j omega 0 t and integrated over the period multiplied by 2 over t naught, and similarly b j corresponds to the coefficient of basis function sine functions, and we take the projection along sine function, and suitably a j and b j can be defined. And a 0 comes from the mean value theorem of the function, mean value theorem, and it is twice the average value of the function over the period, over one period. So, with this we complete the complete representation. So, f t, if we can arbitrarily approximate to any arbitrary degree of accuracy. So, any periodic function of period t naught having finite energy and finite number of, at most finite number of discontinuities within a period, they can be expanded as a summation of sine and cosine, linear combination of orthogonal harmonic functions. So, let us take a simple square wave, periodic square wave, and let us say function g of t is defined as minus a naught for period ranging from minus t naught by 2 to t is equal to 0, and for the other half for period 0 to t naught by 2 it is a 0, positive a 0. So, it is negative for one half of the period and positive for other half of the period, amplitude being same. So, it is square wave. So, for a square wave, so the average value is of course going to be 0 over one period. So, it follows that a 0, that is related to twice the average value of the function. So, a 0 is equal to 0, and secondly the function we can see that it is an odd function. So, odd function will have projection or will have a component only along the odd functions. So, odd basis functions. So, a cosine term which is any cosine term which is actually a even function. So, they cannot represent any odd function. So, we can avoid unnecessary computation trying to find out components of a 1, a 2, a 3 and then evaluate something that is approximately equal to 0 rather than straight away ignoring it by first principles argument that any odd function cannot have any representation in terms of even function. So, now we look at by these arguments we can represent g t as a Fourier series approximation as just sine terms, sum of sine terms. So, j is equal to 1 to infinity b j sine j times omega t, j omega naught t. Now, what are these functions coefficients b j in this particular case? So, we can find integrate, allow the integration and work out the integrals and coefficients. So, this is the representation that we have, successive approximation. So, original function that we have this square wave. So, minus 1. So, we this is of course scaled with respect to a 0. So, we consider unit amplitude square wave. So, minus 1 to plus 1. So, for half of the period it is minus 1 and for other half of the period it is plus 1. and if I use only one term approximation, so this yellow wave, so this is one sine wave and that approximates, that is one term approximation for the square wave. And if I add one more term, so this becomes blue curve, that becomes the new approximation. So, as you can see, the first term that gives us the basic trend of the waveform, and second term that is added, it adds the to the detail, it tries to fit the basic trend to the detail of the waveform, original waveform. So, two component, it tries to model the square wave pattern, and if I add one more term, again it tries to model, I mean it tries to push the wave, I mean broaden the peak and tries to model this flat portion of the square wave still further by pushing this peak to the either end. And this will keep on happening as I keep on adding more and more number of terms. So, this approximation of the waveform will become better and better, and as we can all see that this is a discontinuous function, there is a discontinuity at time t is equal to 0, and the Fourier series approximation converges at the average value of the discontinuity. At the point of discontinuity, the Fourier series approximation will converge at the average value of the discontinuity, and which suits us for this purpose. I mean average value is 0 and that is perfectly fine. Another thing that we need to notice here, this error, maximum error in approximation, this overshoot that happens, that magnitude of overshoot never decreases. It is overshooting this amplitude by this amount, that same the degree of overshoot remains the same for 2 component approximation, it is the same level, for 3 component approximation it is also the same level, and this is called the Gibbs phenomena. So, this overshooting will at the point of where that will happen wherever there is a point of discontinuity. So, at the point of discontinuity there will always be an overshooting, and that overshooting can never be removed irrespective of number of terms included in the approximation. But at other points, so two things happen at the point of discontinuity here. One, the Fourier series converges to the midpoint of the average value of the discontinuity, and secondly, at the point of discontinuity there is an neighborhood of discontinuity, there is going to be an overshoot, and this is this degree of overshoot is not going to decrease by any increase in number of terms. So, that kind of error in the neighborhood of discontinuity will always be there in case of Fourier series approximation for periodic functions with finite discontinuities. So, coefficients, I mean these coefficients that we see of these 3 waveforms. So, the coefficients of these waveforms B1, B2, B3 they can be evaluated by using that inner product GT times sine twice j by T0, j is the integer harmonic integer, and they can be evaluated. So, we can simply split it into 2 parts, I mean minus T0 by 2 to 0 and from 0 to T0 by 2, and evaluate the integral, and that leads to this expression definite integral, and after evaluation of limits we get this cosine in terms of cos of pi j times pi, and that leads to simple expression. So, we have only odd number of terms. So, odd number harmonics are going to be present and even number harmonics will not be present. So, that means the function is of such form that it does not have any representation along the even harmonics. So, it is equal to, if we can evaluate this, it is equal to 4 a naught over j pi for j is equal to 1, 3, 5 etcetera, and 0 for j is equal to 2, 4, 6. Now, one thing that can be seen here is the relative magnitude of this these coefficients b j. So, this is largest for j is equal to 1, because j is in the denominator, j figures in the denominator. So, it is largest for j is equal to 1, it becomes progressively smaller as j increases, and that is a common theme for any representation, generally for any kind of approximation. So, the major Lyon's contribution comes from capturing the trend, the basis function which captures the trend, that has the maximum contribution. Rest of the functions they only add to the detail, and they are only doing very fine work of modifying the local details. They do not really contribute significant energy to the function itself, and that is why for engineering analysis we can get a reasonably good idea by looking at only a few number of terms. So, we may not be interested in a very accurate representation of the waveform, as long as we can model the amount of energy that is going in, and with reasonable degree of accuracy, then that is good enough for our purposes. So, at the point of discontinuity t is equal to 0, the Fourier series approximation converges to the average value of left and right limits of the function, and in this particular case it evaluates to 0. And of course, in the neighborhood of discontinuity there is going to be ripple and overshoot, and that cannot be avoided irrespective of how many terms we include in the series. So, this is what we did for periodic function, and for periodic function I will again go back to the definition. So, for periodic function this is the definition of Fourier series. Now, what happens if I look at a function which is non-periodic? The function that we looked at here, so this is a non-periodic function. So, how do I deal with a non-periodic function? So, let us turn around the argument over its head and let us call a non-periodic function such that it is a periodic function whose period is infinite. So, t naught tends to infinity, right. So, if I look at this Fourier series definition and I treat this as a the function f t as a periodic function with whose period approaches infinity, t naught approaches infinity, then this omega naught, because t naught approaches infinity, then omega naught becomes infinitesimal. So, it reduces to d omega. So, infinitesimal quantity. So, in the limit as t naught tends to infinity, so 2 pi by t naught approaches infinitesimal. So, it is a continuum, it becomes a continuous variable, and this summation then converges to transforms to converts to the integral, and then I have f t is equal to minus infinity to plus infinity f omega e to the power I omega t d omega. And conversely I can define and these are called Fourier transform pairs. So, this Fourier series that we had earlier, a 0 by 2 plus sigma j is equal to 1 to infinity a j cos j omega naught t plus b j sin j omega naught t. So, this transforms. So, this Fourier series gets transformed to an integral transformation, and we can relate this f omega as a combination of a j and b j. What we are computing as a j and b j, and cos j omega t and sin j omega t, they are of course related to complex exponentials e raised to the power I omega naught t. So, omega naught becomes d omega. So, we will see how this transition happens, and of course, this is what we call as Fourier transform, and this is how it is expressed. I mean, of course, this is in continuous functions. F t is a continuous function of time, f omega is a continuous frequency function of circular frequency omega radians per second, and they can they are referred to as Fourier transform pairs. F t can be transformed to f omega, and f omega can be transformed to f t as long as the functions exist, as long as the Fourier transform is defined under the limiting conditions that we know. It has to have finite energy and finite number of discontinuities. So, we will now look at the issues, I mean how Fourier series becomes a special case of Fourier transform, or how we can derive Fourier transform as a limiting case of Fourier series as taking period t as approaching infinity. And once we are comfortable with that, then we will see how to adapt it for use on a digital computer. So, that is what will be the focus in our next lecture. Thank you.